Okay, so let me begin, like everyone, in thanking the organizers for inviting me to speak at this sort of wonderful landmark conference and also in this grand venue. I'll be talking. My talk will be based on some work we've done with Matthias Gaberdiel, which will appear tomorrow, I guess, but. Or rather in a couple of hours from now. But I'll also draw on some earlier work which Matthias talked about in last year's Strings conference. So let me start with a question. Why are we studying higher spin theories? So for string theorists, one possible reason, or one important reason, at least for me, has been the following. We know that free Yang-Mills theory has a tower of conserved currents, which by the usual ADS-CFT dictionary is dual to a tower of Vassiliev higher spin gauge fields. And this has been believed to be a part of the large unbroken symmetry phase of string theory. There's been this belief going back to several decades that there's an unbroken symmetry phase of string theory in which sort of the extended gauge symmetries of string theory are unhinged. So this tensionless limit, or the dual to the free Yang-Mills theory, is potentially a place where you can see a large part of this unhinging. So the question I'll sort of concentrate on in this talk is whether these Vassiliev higher spin symmetries can help us to get a handle on these extended stringy symmetries in this tensionless limit. And the particular case we'll focus on is the ADS-3 case. And I think this might be a good test case because for several reasons, but at this stage, let me just mention that all of you know that it already has this extended Virasoro symmetry, and in the presence of higher spin gauge fields, that's extended to a W infinity symmetry. So it's already a lot of symmetry you see when you have the Vassiliev higher spin gauge fields. But this is in the context of the pure higher spin theories. But if you want to look at string theories in ADS-3, the analog of the free Yang-Mills theory has long been believed to be the free point of the symmetric product CFT for the D1, D5 system, something that Nick very helpfully sort of reviewed a couple of talks ago. And this is the point, or this free symmetric product CFT is the one that you might believe to be dual to the tensionless limit of string theory. So the idea in this talk will be to try to address these questions in the context of this D1, D5 system, or specifically the symmetric product CFT. So since it's been a long day and I guess your attention is fraying, let me just give away the punchline right away. And so in a very precise sense, I'll try to convince you that the Vassiliev higher spin symmetry, or rather its W infinity extension, organizes the full spectrum, the non-supersymmetric, the full, all the states of the free symmetric product CFT on T4, which, as I said, is believed to be the tensionless limit of string theories on ADS-3 times S3 times T4. So this is the sort of the punchline, but to be a little bit more specific, we'll actually concentrate, I'll sort of focus in particular on the chiral sector, or the conserved currents, and try to address this question that I raised earlier about the extended symmetries in the tensionless limit. And I'll try to show that the chiral part of the symmetric product CFT, which captures all the conserved currents at this tensionless point, can be reorganized, rewritten, repackaged, whatever you wish, in terms of representations of this higher spin symmetry algebra, or this W infinity algebra, in a very specific way. So I'll explain this in more detail later, but just to give you a preview, this is the left-hand side is the vacuum character of the symmetric product CFT. So it contains all the chiral currents, the conserved currents of the symmetric product CFT. This is something that can be evaluated using all the techniques of symmetric products. And the right-hand side is a sum over characters of W infinity representations, more specifically representations of a 4,4 Cassette CFT. So these are sort of W infinity characters, and they come with certain multiplicities which are very precise finite group theory multiplicities having to do with multiplicities of the symmetric group appearing in a representation of the unitary group. So one way to interpret this equation is to view this as an infinite extension of the W infinity symmetry, in the sense that the simplest term in this sum on the right-hand side, where lambda is the vacuum representation, corresponds to the original W infinity currents, but there are an infinite number of other currents which sort of extend this symmetry. And you know what they are. You can be quite precise about them. The vacuum character, as I said, contains the usual W infinity generators. These are bilinears in the free fermions and bosons that make up the symmetric product CFT. But there are infinite number of other additional chiral generators corresponding to various non-trivial representations of UN. And you can write down the W infinity primary currents corresponding to them. I've just written down a couple of examples. Oops. So these are a different set of bilinears, but then there are other terms which are quartic, etc. So corresponding to corresponding to a class of these representations, you get these additional chiral generators. So to understand where these results sort of come from, I'll have to take you through a little bit of a detour through the so-called world of large n equal to 4 supersymmetry. So string theory on ADS 3 times S3 times T4, the case we are studying, has what is called small n equal to 4 supersymmetry. That's the conventional 4,4 superconformal symmetry we normally encounter. But it will be useful to come to this theory via a limit that involves the so-called large n equal to 4 supersymmetry, and in particular through an example of a higher spin holography, one of these vector holographies involving Cassette conformal field theories having large n equal to 4 supersymmetry. Now, what is the large n equal to 4 superconformal algebra? Well, it's the two-dimensional superconformal algebra with 4,4 supersymmetry, but which has two SU2 Kac-Moody algebras. This is the generic superconformal algebra with 4,4 because you have a SO4 R symmetry, so you have two SU2 Kac-Moody algebras, and therefore there's an extra parameter in the algebra in addition to the central charge. This can be taken to be some ratio of the two levels of the Kac-Moody algebras. And the small n equal to 4, which is of interest to us, arises as a sort of contraction of this large n equal to 4 algebra when you take one of the levels to infinity, so that you're left with only one SU2 R symmetry at the remaining level k minus. Okay, so this is the large n equal to 4 symmetry. And the particular instance of this Cassette holography, all of whose details won't be very important to us, this Cassette holography involves a Cassette CFT. This is a supersymmetric version of it, but this is the bosonic version, so you can focus on this part. The main things to remember is that there are 4n plus 1 free fermions. This is a level 1 theory. And then there's sort of Weisser-Minowitten factors involving SUN plus 2 modded out by UN. And this theory has been known to have large n equal to 4 supersymmetry with levels k plus 1 and n plus 1. These k and n that appear over here are the two Kac-Moody algebra levels. So the central charge takes a specific form, and one can study this theory in the so-called 't Hooft limit, where you study these holographies, so which essentially involves taking this ratio, which I defined as gamma earlier, but it is also what you could call the 't Hooft coupling, keeping this ratio fixed. So as I said, we won't need too much about this, but just to acquaint yourself very broadly, there's on the higher spin side, dual to this Cassettes EFT is a Vasiliev theory, which is based on a gauge group, a higher spin gauge group, which is a supersymmetric version of the conventional higher spin gauge group. Again, the only point you need to really take away is that there are a fixed number of higher spin gauge fields at any given spin. There's basically one supermultiplet for each spin S, and that supermultiplet contains some number of spins, and these are the SU2 labels, etc. So again, that's the these gauge fields generate an asymptotic super W infinity algebra, which matches that of the Cassettes EFT. So this is the sort of, it's these gauge fields that generate the W infinity algebra, which will be the building block for our super conformal, for the stringy symmetries that I'll talk about later. So, okay, so this was the gauge field part of of this holography, but there's matter. So this gauge fields that I had over here, from the CFT point of view, these are part of the vacuum representation of the CFT. They're part of the chiral algebra of the CFT I showed you. But there are non-trivial representations, some of which correspond to, in fact, matter that you can couple to the Vasiliev theory. And so the general primaries are labeled by two essentially representations of the numerator and denominator Vesuminowitten theories. So in this particular case, SUN plus 2 and SUN, or UN rather. What will be important are the sort of family of primaries, which the first non-trivial one of which is one in which this is the vacuum and this is the fundamental representation. And this primary corresponds to the matter multiplet, which contains a scalar field and some spin half fermions. And so this is the matter that interacts with the higher spin gauge fields. And the other primaries of the form 0 lambda, they are multi-particles of this basic matter multiplet. And so you can view this sector of 0 lambda as some kind of a consistent subsector of the Cassette theory. The general diagonal modular invariant Hilbert space of the Cassette theory is one in which you have the general lambda plus, lambda minus, but this is a consistent subsector which you can call in some sense the perturbative Vasiliev multiplet. This general CFT, these general primaries, when you take the large n limit, they contain what are called light states. In fact, there's a continuum, but as we'll see, these will not play a role when we talk about the symmetric product. Okay, so these were maybe a bit heavy about the Cassette CFT, but as I said, what we are really interested in is in the limit where you go to the small n equal to 4 from the large n equal to 4, which is a contraction. And in this limit, things simplify a lot. That's why you don't need to know very much about all these Cassette CFTs that I mentioned earlier. You see the central charge goes to 6 times n plus 1 in the limit. So the contraction is when you take the level k to infinity, as I mentioned. So the central charge goes to 6 times n plus 1. And the Cassette CFT becomes much simpler in this limit. It becomes what you might think of as a continuous orbifold. A continuous orbifold by the group UN of basically n plus 1 copies of T4. So how does to give you a rough picture of where that comes from, remember there were already 4n+1 free fermions in the original Cassette theory. The Wess-Zumino-Witten factors in the large K limit decompactify to give you 4n+1 free bosons, and they combine with these to form a supersymmetric T4, or really R4, but all gauged by the denominator UN. And if you ask for the charges of these bosons and fermions, there are basically 4 of these free bosons and 4 of these free fermions are uncharged under the UN, so they are singlets, and the remaining ones are in fundamental or anti-fundamental of UN. So the thing to take away is that there is this Cassettes EFT, but in the limit, in the large K limit, it becomes a relatively simple object. It may be a little unfamiliar because you have this orbifolding by a continuous group, which you're not normally accustomed to doing, but basically it's the gauging by the UN that this continuous orbifold is capturing. So in the language of this orbifold, you can talk of the untwisted sector and the twisted sector. The untwisted sector are the UN invariant states. So these are the singlets that you can form from the fermions and the bosons. For instance, the simplest one is, again, built from the fundamental, the left-right symmetric one, which would correspond to psi bar. So the i's are the fundamental, anti-fundamental indices of UN, and this is the psi bar state, and in the limit, in this contraction limit, this matches with the fact that these have dimension half comma half. In fact, this whole set of states that I identified earlier with the perturbative Vasiliev states, namely 0 lambda with its complex conjugate, these actually form the untwisted sector of this orbifold. So the UNs, another way to talk about these UN singlets formed from fermions and bosons is to consider this part of the Hilbert space of the Cassettes EFT. And this is very similar to things that Matthias and his collaborators have seen for the bosonic and the n equal to 2 cases. So this was the untwisted sector of this continuous orbifold. The twisted sector is sort of more subtle because you now have twists by UN as a continuous group, and so you have sort of continuous twists, and which in the language of the gauged UN can be viewed as turning on small, arbitrarily small holonomies of the UN, and this is what in general leads to this continuum and these light states, and these are the states, so these are the generic states which are labeled by the lambda plus and lambda minus with lambda plus not equal to 0. These are the, so these form the generic twisted sector, but as we'll see when we talk about the symmetric product, the twisted sectors, the light states will not appear. Okay, so this was sort of preparatory. So now we are ready to sort of try to link this with the symmetric product. We have this orbifold, which you get as this sort of limit of this Cassette holography, but it's a continuous orbifold, whereas what you really want is a discrete orbifold by the symmetric group. So how could you relate these two, or is there even a simple relation between the two? Well, it turns out there is, and the crucial observation is that the symmetric group sits very naturally as a subgroup inside this UN, and in terms of which the fundamental and anti-fundamental of the UN just correspond to the simplest non-trivial representation or the n-dimensional representation of the symmetric group. So if you view these free bosons and free fermions that were charged under the UN in terms of the representations of the symmetric group, they basically, because the n and the n bar correspond to the n-dimensional representations of the symmetric group, you get something very simple. And this is, in fact, how the fermions and bosons of the usual symmetric product transform. By the way, the second index, I should have said, refers to the SU2 R symmetry. So the first index is the thing that tells you about how it transforms under, in this case, under UN, and in this case, under the symmetric group. And you basically have 4n plus 1 free fermions and 4n plus 1 bosons transforming in the symmetric group in the standard way that they do in the usual symmetric orbifold. Since we've identified the symmetric group as a subgroup of UN, the untwisted sector of this UN orbifold, because that's imposing a stronger condition of singlets under UN, that's going to be a subset of the untwisted sector of the symmetric group orbifold, and so this will be important for what follows, because remember I mentioned that, so we put this together with the fact that these representations, which were the perturbative Vasiliev states, this was the untwisted sector of the UN orbifold. We see that this is a very natural closed subsector of the symmetric product CFT. So this tells you that the Vasiliev states form a closed subsector of the symmetric product CFT, and therefore you're sort of, that goes it goes towards confirming that this is sort of this point, the symmetric product CFT is like the analog of the tensionless string theory. But we can do actually much more. The more interesting statements are the fact that all the other states of the symmetric product CFT must also consequently transform in specific representations of the chiral algebra of this UN orbifold, because the symmetric group orbifold is the symmetric group is the subgroup of this UN, so you can actually gather all the states of your symmetric product in terms of representations of the UN invariant currents or the W infinity currents of the UN orbifold. So if we schematically write the full partition function of the symmetric product, these are the usual Q and Q bars, and these are SU2 chemical potentials. The schematic structure is that of a vacuum part, and then there are various untwisted sector states, the non-trivial untwisted sector states that you get from having fermions excited on the left and the right. And then there are, of course, the twisted sector states corresponding to the various symmetric product twists. So the general partition function will stick to the Neuer-Schwarz sector, the perturbative sector. So the general partition function takes this sort of form. And the claim from this general argument is that all the states over here should be organized in representations of this continuous orbifold. So let's see how that works. So in particular, the vacuum sector, the simplest piece over there, can be organized in terms of coset representations from the untwisted sector of the continuous orbifold. The untwisted sector of the continuous orbifold were these representations. So you expect that the vacuum character of the CFT should be a sum over these characters with a multiplicity that is given by the number of times the singlet representation of the symmetric group appears in a given UN representation lambda. Since the symmetric group is a subgroup, each representation of the symmetric group may contain the singlet of the symmetric group some number of times, and these are these positive integers lambda. And so this is the extension of the W infinity that I talked about earlier, and this would include in general bilinear, not just the bilinears, but also cubic, quartic terms, etc. So this was sort of general. So just to have a reality check, we can try to sort of verify this equality, because this is a sort of a very non-trivial. The left-hand side is something that you know from symmetric product technology. The right-hand side is something you know from W infinity characters and multiplicities, group theoretic multiplicities. So in principle, there's a non-trivial identity here. So we've checked this, verified this. You use the usual symmetric product prescription of Dijkgraaf, Moore, and Verlindis to compute the vacuum character, and you can write a Q expansion to as many powers as you have stamina for. And quite remarkably, you can see that it assembles into representations of these of this higher spin W infinity characters. The vacuum character contains all the usual Vasiliev higher spin fields, but then there are additional generators like the ones I wrote earlier, and it just goes on. So even to this order, you see that there are many, many representations and coming with non-trivial multiplicities, etc. So we continue to check for the other states. So for instance, the simplest non-trivial part of the untwisted sector containing one fermionic excitation on the left and the right. This contains some of the marginal operators of the symmetric product. You can argue once again in a similar way that it should be related, it should be a sum of these W infinity characters, but with a multiplicity which is now not the singlet, but the n-dimensional representation. So you do it again, you compute the left-hand side using the DMVV kind of prescriptions, and once again, this is just meant to show you that things agree quite non-trivially with all the non-trivial multiplicities of 5s, 7s, 9s, and so on, as far as we could calculate. So finally, about the twisted sector, this was the sort of the other part, which is also interesting because it contains the other marginal operators, so that, once again, you can write it slightly more complicated in terms of the representations that appear, but once again, you can check. So it does seem that you can reorganize the spectrum, and in fact, you can refine this into single and multiparticle states, etc. And if you take the generators corresponding to the single particle currents, and it's useful to view the free fermions and free bosons as Cartan elements of an adjoint field under which the symmetric group is the usual Weil group action, then these correspond to sort of higher order traces not just of bilinears. So you can view them as sort of higher Rajesh trajectories compared to the leading one, the Vasiliev states. And as I said, there are no light states, in a symmetric product, there are no light states about the vacuum. And from this point of view, that arises because these states are not local with respect to this extended algebra that you have, this extended stringy algebra. So that's why the light states don't appear in this partition function. So let me just summarize. So what we've done is sort of identified the Vasiliev states as a subsector of the symmetric product CFT. So sort of to encapsulate it in a slogan, the vector model holography in which you have the Vasiliev gauge fields, it corresponds to the UN orbifold, whereas the matrix-like holography of adjoint fields corresponds to a symmetric orbifold. And using this, we've assembled the full spectrum in terms of representations of the W infinity algebra, and in particular, the massless states of the chiral sector in terms of this huge unbroken symmetry, stringy symmetry. And just to look a bit ahead, I think one of the very interesting things would be to understand the Higgsing of this symmetry, because you can now deform by these marginal operators away from the tensionless point. You know what representations of this bigger symmetry group they transform in. So hopefully that should give you some control over these deformations. It remains to be seen how strongly does it constrain the spectrum, 3-point functions, etc. Whether there's relation to the integrability that people study. We've started off trying to understand the string theory on this background, and we hope that we can apply similar techniques to this case. And there are intriguing similarities to the talk that Leonardo gave yesterday about the W algebras in higher dimensions and to other higher dimensional sort of stringy embeddings of higher spin theory. So these remain to be explored later. Okay, thank you very much.
Okay, we have time for a few questions.
So maybe you mentioned, and I missed if that was the case. Do you have a way of determining the multiplicity of W infinity algebra?
Yeah,
And
those n of lambdas.
Yeah.
That's a group theoretic question. It's a finite group theory question, which unfortunately we haven't found a good mathematical reference to. But take a UN representation lambda. You have the symmetric group as a subgroup. Find out how many times the singlet representation or the n-dimensional representation or any other representation occurs in that. We've done that we have some algorithms to determine that, and that's what went into in these tables over there, and we've cross-checked it with other things, so yeah. But it would be nice to have a nice closed formula for that and verify those identities sort of analytically, but that we haven't done.
Is there a reason why you use SU2 currents to get the large n equal to 4 theory? Like, why do you use SU2?
The SU2 is a part of the large n equal to 4 algebra. It's part of the SO4 R symmetry, and so there are two SU2 Kac-Moody algebras in the large n equal to 4, which contract to one SU2. The n equal to 4, you mean because the ADS 3 times S3 times T4 string theory has a 4,4 supersymmetry in spacetime.
Did you also have questions on that side?
Did you also investigate representations of the isometry algebra, PSU 1,1/2 square, or only of the higher spin one?
Yeah, I mean, that's part of the W infinity.
The branching.
Yeah, the SU 1,1/2 is part of the Virasoro, which is part of the, super Virasoro, which is part of the super W infinity. So all that is in the W infinity representation. So you can break up the W infinity primaries into primaries of the global group, but yeah, that would be, of course, an infinite number.
Okay, my question is it clear what is, from the bulk perspective, what is an extension of this higher spin algebra that follows from your boundary construction? And what is the relation
you're probably in a better position to say, but yeah, it's interesting that there are all these additional gauge fields which are in specific representations of the original higher spin algebra, and they presumably form a consistent interacting system, but which is in some sense the string field theory of the system, but yeah, but I don't have any good insight about.
Okay.
Okay, other questions? Yes? There?
So you discussed the symmetric product, but maybe I missed it, but if we resolve the symmetric product by turning on the moduli,
yes.
How much of this survives?
Yeah, so generically you expect to Higgs most of these because for instance, the Z2 twisted sector, the marginal operator in the Z2 twisted sector, which corresponds to turning on a radius, is a particular charged representation of this W infinity algebra. So giving that an expectation value is like Higgsing this symmetry, so that's what we would like to understand, whether by Higgsing the symmetry you still can constrain whether knowing that it's part of this bigger stringy multiplet can help to constrain the spectrum or correlation functions moving away from this point. But yes, I don't have a concrete thing to say.
Okay, one last question. I think there was one there. No? Well, if there is no other questions, that closes the session, and let's thank our speakers again.